Let's start. Welcome everyone. Welcome to our monthly ICG invited talk series. It's a pleasure to introduce Markus Steinberger. Markus is assistant professor at Graz University of Technology at the moment. He's leading the group which is doing GPU scheduling and visualization. He has an MSc and PhD from Graz University of Technology, and after a short postdoc phase at TU Graz, he moved as a junior group leader to Max Planck Center for Visual Computing and Communication in Saarbrücken. And before that, I forgot to mention, he got his promotion as Sub Auspicius Presidentis, which is a nice achievement. And after his junior group position at Max Planck, he moved back to Graz University of Technology to have a group there as assistant professor. And Markus is going to talk about adaptive GPU scheduling, and we're looking forward to the talk. Thank you.
Thank you very much for the nice introduction. Yeah, I'm going to talk about our work on adaptive GPU scaling and also two applications for that. And the talk will be kind of structured in this three parts. That I will first tell you about how a GPU works in general, just a tiny bit, and about our adaptive scaling approaches, and then we'll come to two parts in terms of applications. Okay, I guess I will just start with the first part. This has been a secret major paper, which is titled Whippletree, and this will deal about how we can go ahead and use the GPU more dynamically. Okay, I guess we'll just start by talking in general about how GPUs work, and then we'll go into more detail how our approach works. I can quickly ask how many people have worked with CUDA already? Yeah, perfect, so there's not too much I have to tell you, it's good. So the idea is we've got a GPU, and I guess you then all know that a GPU consists of multiple single instruction, multiple data units, and they are strung together into multiprocessors, and every multiprocessor has got some local shared memory attached to it, which means this is memory that can be accessed in a kind of fast way. And then we also have got some global memory, which is further out. And if you would go ahead and program something for the GPU, you would usually go ahead and program from the view of an individual thread, and you would just write code that this thread would execute. You then have to know, however, that these threads are strung together in what is usually called a warp, and this matches the SIMD units on GPU. So there are a couple of threads which execute on the SIMD units, which means they all have to execute the same code. And as soon as they execute different code, it's not going to be efficient anymore because the execution needs to be synchronized. And then you would go ahead and if you start execution on GPU, you would start blocks. And blocks are just a collection of warps which land on the same multiprocessors. And which means that they are able to communicate efficiently with this local shared memory that we have here, and they can cooperatively work on some kind of objective. However, you usually have to go ahead and launch enough threads for the entire GPU, which means you need to have enough parallelism. And the way you would usually do it, if you go ahead and if you use CUDA, as most of all know, is that you would launch a large grid of blocks. And this means you would just go ahead and launch one big kernel where all of the threads start executing the same code. And this is the traditional way of doing things. And what you can do, however, is you can change the size of this grid, and you can also change the size of the blocks. This is all that you can adapt. And you have to go ahead and launch a large grid to be efficient to provide enough parallelism. I guess that's straightforward to follow. Right? Yes? No? Oh, good. Okay, so this programming model is kind of straightforward to use if you go ahead and if you do image processing. So what you would do is you would just go ahead and start an individual thread for every single pixel, and in this way you get good performance because this is what this programming model is actually made for. If you, however, go ahead and want to do something more complicated, then you already run into problems. And one of these examples would just be the traditional rendering pattern. So if you, for example, would want to go ahead and just do the rendering pattern in software, you would say, okay, I've got a GPU. The GPU is usually used for real-time rendering, so I should be able to also go ahead and write a simple rendering application with this kernel-based programming model. And then you immediately see that this just doesn't work because you have these different stages. For example, vertex shader, fragment shader in the back. You would have some rasterization and so on in between. And if you would just want to do that in software, you would immediately figure out that doesn't work because you cannot just go ahead and launch one grid or one kernel for all of that. You have these different parts, and you kind of have the data which is streaming from this pipeline, and you would have to execute the different stages dynamically, and so this just doesn't work. And this was kind of one of the motivations that we used back then to motivate our work, and we figured, what can we actually do about it? What can we change to allow a more dynamic use of the GPU, because we know that the GPU, for example, is able to execute parts of this pipeline efficiently. So the hardware should usually provide enough features to do that, but something is holding us back. And we kind of figured out that the thing that is holding us back is this rigid setup of the grid. Because we know that we need still to have threads and warps and blocks because they kind of match the low-level hardware. This is what I mentioned in the beginning. But the grid is kind of an arbitrary thing which is set on top that you just launch a big number of threads, and that's it. So we figured we should probably just try to change the execution model and scheduling model, and in this way we can probably use the GPU in a more dynamic and better way. And the idea is that we just want to be able to launch these threads, warps, and blocks kind of dynamically. So you can think of an algorithm which just starts at some point on the GPU, somehow parallel in the beginning, and then dynamically we figure out, okay, there's something the single thread should be working on. And something pops up where we would want to have a single warp working on. Or something pops up where we say, okay, we need more threads for that, we want to dynamically launch the entire block. And that's the idea of the Whippletree programming model. And then the question is just, how can we do this? How can we come up with such a programming model and execute it efficiently? And this is something I will just explain to you quickly, that you have got an idea how that can work, and later on we'll just go ahead and develop something on top of that. So the idea for supporting this dynamic execution is that we somehow have to take control over the GPU. And to do that, what we usually do is we just launch a big kernel still and kind of overtake all of the processing units. So we just launch a couple of blocks on the GPU and completely fill up the GPU and now do everything dynamically in software. And we just call these blocks worker blocks. And the idea now is that we have the work queues where we temporarily store these individual threads or warps or blocks that we want to start. And we just collect the work that should be executed at some point within these work queues. So you can think about you're executing your program somewhere, and then you say, okay, here is another thread that should execute at some point. Then we could store information about that in one of these work queues. And the idea then is that our worker blocks, they just keep executing in a loop, and they keep occupying the GPU, and then we can dynamically decide what we want to do. And we then figure out where there is work available in these work queues and just draw work in and then execute it. And in this way, we can also dynamically adjust the number of threads to these work items or tasks. And for example, if we have got individual threads that should be executed, we can draw in more concurrently to start the execution. If we have an entire block, we might just draw in one work element. And this is the overall idea. We can also then dynamically generate work again. While we're executing, we can just put tasks into these work queues, which will then be pulled in by another worker block for the execution. So in this way, it allows us to dynamically decide what should be executed and also have these different tasks that can run concurrently on the GPU efficiently. And what we also get is that we are grouping them together in these different work queues, which means that we can draw in the same type of task. And as I mentioned before, on the CMD units, it's important that we execute the same code. So if we go ahead and draw in the same tasks, it's rather likely that we execute the same functions, and in this way you get good performance. So that's the overall idea. And as I mentioned before, we can dynamically generate new work, and we also can do load balancing by dynamically then deciding from which work queue we want to draw our work. And so we can actually build quite a lot of things on top of that. You can come up with different scheduling algorithms. You can go ahead and map many more problems now for the GPU. And that's the overall idea behind this model. What we additionally get is that we can also use the local shared memory that we have on the multiprocessors to store immediate data. And in this way, we don't need to go out into these global work queues. We can stay locally with the data. And this means we would at first go ahead and see if we can store data locally that has been produced in a local work queue. And then when we start the execution, we would simply go ahead and pull in these elements from the local work queues first. If we don't have any work locally, we just go to the global work queues. And that's the overall idea. And as I mentioned, we can build quite some algorithms on top of that. Okay, I should quickly mention that we can actually go ahead and implement the same execution model or programming model in a different approach, where we still have these work queues on the GPU, but we could simply start a controller block which monitors these work queues, and then from the GPU dynamically with the parallelism goes ahead and launches worker blocks, which then again pull in the data from these work queues. Which is a slightly different approach. It has got some advantages and some disadvantages, and I'm not going to go into detail here, but we have the option to simply switch out the way we execute. And that's kind of important when you want to go ahead and tune your performance, that you have got these different options to see which one works better for the problem you have at hand. Okay, this is all I more or less want to tell you about this first part. And all I want you to take away from that is that by changing the programming model, we can actually go ahead and have a more dynamic execution of the GPU. And we can go ahead and implement that model in software. And we actually found out with a couple of applications that in this way we get way more performance for certain kind of algorithms which usually don't fit the GPU too well. So if you would just go ahead and do image processing, you probably don't need that approach. But as soon as you have got problems where tasks or things are popping up dynamically that should then be executed by different numbers of threads, then this model makes a lot of sense, and we show that it helps you a lot to run this kind of algorithms on the GPU, which usually would not fit the GPU too well. Okay. Probably should also mention that the kernel-based programming model is more or less just a special case of this programming model, where you just start all of the blocks that you want to execute at one point in the beginning, and that's it. So there's actually a lot of potential to implement that programming model a little bit more in hardware. And we can actually see that with the upcoming architectures, NVIDIA might go in this direction a little bit. Okay, so much about this first part. Any questions so far? Anything which is unclear?
What would be application examples for those algorithms that usually don't fit on the GPU?
The two things I'm going to show you next. Another thing, or let's say this in general, any kind of problem where you have got some kind of hierarchy, where you start out with only a little bit of parallelism, a little bit of information, and then you traverse down a tree, or also you traverse through a graph, for example, where you want to go ahead and have different amounts of parallelism for nodes. These are all examples that fit this approach really well. And the two things I will show you now actually go from this domain.
How do the individual workers need to synchronize each
other? The individual workers. So the thing is, let's go back. The main way of communication would just be through these work queues. So the idea is you could mostly go ahead and implement the algorithms just in this way, that whenever you execute something, you produce a new task, and this is going to be placed in the work queue, and then another worker can pick it up. So this is the most straightforward way. If you want to do more, for example, you want to introduce some dependencies in the execution, you could have that too. then we would do that explicitly in a separate memory, in global memory, where we, for example, could use atomic operations to increase counters, decrease counters, figure out how many depending tasks are still waiting, and then just start the execution as soon as all of the dependencies have been completed. More if you would want that. So especially when you go ahead and you occupy the GPU fully, you can potentially also implement locks if you do it the right way, and then you can do more or less arbitrary communication. If you want to communicate within the block, it's actually pretty straightforward because then you're on the same multiprocessor and you can use synchronization and shared memory is only multiprocessor itself to communicate to.
And for example, if this local memory is shown here, so it's more as prefetching the next task which should be executed as far as I understand.
Yeah, so with this local shared memory, we usually don't prefetch. It's just when we produce something, we would first put it locally and then just take it out of the local memory.
And just wondering, because if you have multiple queues, how do you show in total that all of them more or less are done in the end? So it's not one is blocked or whatever.
Yeah, so this is actually one of the kind of more interesting things to make sure that everything is completed, because you could have the case that all of the queues are empty and only a single one is working still, but this one might then produce new tasks, which again could fill up everything. For this, you need some kind of communication between the workers. So this is simply done by some atomic counters and having two states in our case, where we first go into the state where we believe that we can be done now, and then just wait until every single other block confirms that state. So that is true. Okay. If there are no more questions about that, I will just go into these two example cases. I hope they're going to be interesting. One is called efficient hierarchically sparse matrix operations on the GPU. This is something I just presented last week at ICS. So this goes a little bit more into linear algebra. Linear algebra can actually be used for quite a lot of examples, which actually also listed here. And I will just give you a quick introduction into sparse matrices at first, if not everyone knows what a sparse matrix is. Does everyone know what a sparse matrix is? Who doesn't? Okay. Looks like everyone knows it. Just really quickly, sparse matrix, we have got loads of zero entries, and we are just interested in the non-zero entries. So for example, we can have a matrix which is 1 million times 1 million, and then we only have 3.1 million entries, which means we only have about 3 entries on average per row, for example. And then we don't want to store all of this explicitly as a full matrix, but we're just interested in the non-zero entries, because when we go ahead and do operations with them, they are the ones which will matter. And sparse matrices actually used in loads and loads of problem cases, for example, in numerical analysis, graph theory, large-scale simulations, and so on and so forth. So there are many, many use cases for it. And what we were trying to do is we said, okay, let's see what we can do with the GPU in terms of this sparse linear algebra, because GPU has that high performance. We now have got a proper floating point model. We have that kind of fast memory. We have got a proper cache hierarchy, so we can actually build more complex algorithms. We have got larger memory now, so we can actually deal with bigger problems. And we can actually go ahead and build supercomputers out of it. And so this was just the motivation for why I want to use it. And now I will tell you a little bit of the difference between how sparse matrices are usually handled on the CPU and on the GPU, and then tell you why I want to go into a different model for them. So here we have got a sparse matrix again, and I will now tell you how you can store it. So the most straightforward way of storing such a matrix is in the so-called coordinate list or COO format, where you just go ahead and store the row IDs, the column IDs, and the values. And with this triplet, you can then identify where in the matrix you are and what value you have. So, for example, row 0, column 1, element 4, we see this entry, row 3, column 2, has a 9, and so on and so forth. So this would be the straightforward way of explicitly storing all of the entries. Well, this is kind of straightforward. It's definitely not the most efficient way of storing it, and the most common way, I would say, to store such a matrix is in the compressed sparse rows or columns format, where you go ahead and you sort the entries, for example, according to rows, and then instead of storing the row indices explicitly, you can just say row 0 starts here, ends here, and in this way you don't need to store 0, 0, 0, 0, 0, 0, but just the beginning and the end, which is kind of straightforward, but for that the data has to be sorted. And then you would get this kind of representation that we can see here. So I guess this is the most well-known format and the most often used format, but recently we actually saw on the CPU side that a lot more block-based formats were coming up. And the idea here is that if you have got a matrix, you probably want to store data elements which are close together, also close together in memory. So for example, here we could store these three together if you would make a block-based format. And this usually has the advantage that you then can go ahead and access data which is close by also efficiently. Because if something is close in memory, you can access it more efficiently because it might be on the same cache lines and so on and so forth. And on the CPU, we see block-based formats where we store the matrices as dense arrangements of sparse blocks, as sparse arrangements of dense blocks, and even as a hierarchy of blocks. And there you can even have different node types. So we have seen all of that on the CPU. On the GPU, however, we haven't seen any of these hierarchical formats yet, and all of the block-based formats are mostly for special operations. So, for example, for sparse matrix vector multiplication. And this is also the case when we go ahead and compare Kernel-based. So on the CPU side, we have got full hierarchies for these matrices. In this way, then have got efficient access along rows and columns. We have got a lot of considerations about how efficient it is to store data in such a hierarchical format because it can reduce the bits for storing individual indices. And you even have got formats which support many different operations in these block-based formats, and you can dynamically change their matrices there. If you go to the GPU side, however, we only have got the flat two-level hierarchy. So this means you just have got the blocks arranged linearly in memory. And all the considerations we have there, and most of them, are just for optimizing simple operations, like, for example, matrix vector multiplication. And what these formats then do is they spend loads and loads of time on pre-processing, just to arrange the data optimally in memory, that when you then do the multiplication, you're fast. And this pre-processing can be 150,000 times stronger than the operation itself. And also, due to all this pre-processing, the matrices have to be completely static. So in this work, we were kind of asking the question, can we close this gap between CPU and GPU and have actually a hierarchical block-based format for the GPU, which works efficiently? And this was the overall idea, and you can already see where I'm going with that, because this kind of fits this programming model that I mentioned before, probably. What this would allow us is that we can have local changes of the matrix, because if we have got such a hierarchy, we can just change individual parts in the hierarchy, and in this way change the matrix. We can then have efficient access along rows and columns, which we did not have on the CPU yet either, and we can combine different block types. So we can change our representation within the hierarchy to adjust for local patterns that we see in the matrix. And of course, we want to be able to run standard operations efficiently. This is the overall idea. And what we also want to do is build new matrices efficiently. So if you go ahead and have the matrix operations and you combine two matrices, you want to be able to build this new matrix efficiently. So these are kind of the requirements. So let's talk a little bit about the format that I was already kind of implicitly describing. So the format should be a hierarchical one where we have individual blocks on the different levels, and the data will usually be sparse. So we will have sparse entries on the higher levels of the nodes, and then when we come to the leaf nodes, we have got the actual data, which will be some floating point values usually. So that's the idea. And we can then go ahead and store the data for these sparse nodes in a local format, which is just this scriptets again. And we also support dense nodes, so we just store the entire data in terms of a linear way. So this is the overall idea. And the nodes we usually choose to be quadratic with a size of d times d, and then we can just choose d differently to figure out what is efficient in terms of storage and execution. So a small example how this would look like in memory, the same nodes that we had before, but now just how we store it. So this root node here would just have the two entries and a pointer to the next node. The next node then has got two entries here with the coordinates and pointers to leaf nodes. And then the leaf nodes in the core format again have the coordinates and the values, or as a dense node simply from the line in memory. And then you would have these four elements just one next to each other in memory, and using the pointers you can construct the entire hierarchy. This is the idea. But the nodes don't have to be sorted in any way, they can just be somewhere in memory because we're actually using real pointers. So that's the overall idea. And what does this format enable? So first of all, with such a hierarchical format, we can go ahead and store these matrices more efficiently. So if you compare the memory requirements for the core format versus the CSR format versus our format, we can see that usually CSR is about 80% of the core format, and our format is usually a little bit more efficient still. And in this way, we can then handle larger matrices because we don't need so much storage. Why is this the case? Because when we have got our nodes, we can just reduce the number of bits that we have to store the coordinates because they are of limited size. And this gives you then overall reduction in data size, although you store the pointers additionally. Okay, so much about the storage reduction, which is an important point if you really use data format, but in terms of execution, it's not so important. If we go ahead and now consider what do we have to do if we want to go ahead and execute an algorithm on top of this format. This means that we first of all have to go ahead and traverse the hierarchy, and we then also need to go ahead and work with the leaf nodes that we had. What does this help us? So first of all, when we, for example, want to transpose a matrix, which is one of the really common operations that we need to do, all we need to change is the way we index the data. So instead of taking the row ID and the column ID, we just switch the two around. And also when we traverse the data in the leaf node, instead of traversing it in this way, we can simply traverse it the other way, because we know how it's stored in memory. If we, for example, would have to do this transposition explicitly, we could also grab the data, store it in shared memory when we work with it on a multiprocessor, transpose the data, and continue working with it, just in case it is needed. We can also do additional things like we just have two matrices which might share some kind of common subpart because we only change some elements in one matrix. Then they can just share this entire subparts of the hierarchy. We don't have to explicitly store the two matrices, which is something that we would have to do if we used any other format. And we can also support dynamic changes. So we could just go ahead and say, okay, we want to replace this node here now by another dense node with this and this elements. We don't have to change anything else, just the nodes that are actually changing. So this is a large advantage over previous formats. What we need, however, is memory allocation on the GPU, because otherwise we cannot build new matrices efficiently. Okay, so let's come to the fact that we actually want to do something with these matrices. So one of the things you want to do is run any kind of algorithm on top of that, which means, as I said before, you have to traverse the hierarchy, and we want to do it efficiently. And for doing it efficiently on the GPU, we have to consider how many entries we have in the different nodes. And here you can already see why this fits our execution model from before well, because we might, for example, go ahead and store start a single thread for the root node here, and this thread would then want to spawn two new threads which work on the next node, and this thread would then spawn maybe 3 threads for working with this leaf node here, whereas we could use 16 threads, for example, here. And depending on how many entries we have, we would want to dynamically decide how many threads we want to start and execute here. And this is something you cannot do efficiently with previous programming models. You need to have this dynamic or adaptive scaling. So that's the overall idea. So if we just think about it a little bit more, what this means is we will have different queues in global JKU memory where we store information about different entries. We can also group them a little bit according to how many threads we want to start from them to be a little bit more efficient. And then we would just hand it over to the scheduler and say, okay, here is the root node, here's the information I want to store for execution. Now start the scheduling with so many threads. And then we will dynamically put new elements into these queues by handing it over to the scheduler, and the scheduler will then execute for us. So that's the overall idea. And the good thing is we also have got this work aggregation into memory within the queues, so we will also then go ahead and start a sufficient number of threads together for efficient execution to avoid thread divergence. So that's the idea, and I will quickly show you what performance you can get with that and discuss it a tiny bit. So one thing that we implemented is sparse matrix vector multiplication, because this is kind of the most common thing you need to be able to support, to have a sparse matrix multiplied by a dense vector, get another dense vector out. And this is used in, especially in iterative solvers and so on and so forth, so many people are working on that. And it's really quite straightforward. We just reverse the hierarchy. When we end up at the leaf nodes, we do the multiplication of the matrix element with the input vector element, and we add it to the output element. And we do this with an atomic operation because you can have different nodes in the matrix that will then end up adding something to the same element. And we can very efficiently go ahead and consider transpose operations, because all we have to do is switch the row ID and the column ID when we are considering the leaf nodes. So that's really straightforward. And this is just what I described, and of course we first have to traverse the hierarchy, which is straightforward. And the second thing that we implemented is a simple addition. So we take a matrix A, we add a matrix B, and we get a new matrix C out of it. And this is a little bit more difficult if you think about it, because now we have the two matrices that we want to traverse in a combined fashion. So instead of storing individual nodes in our task queues, I'm not going to go back, we need to store a combination of two nodes in the task queues. But that actually works trivially easy because our queues can be completely configured. So this is no problem. However, what we have to think about is that actually generating this new matrix is not so trivial, because we beforehand don't even know how much memory we'll need, because it depends on how many overlaps in terms of nodes we have. And when we generate new nodes, we at first also don't know how much memory they will need, because it depends on how much overlap there will be again. So it's actually not so straightforward, but we implemented all of that. And some considerations here: if we have got nodes which are only present in one matrix, then we can simply copy them to the output. If we have got a dense node where we add another sparse node on top of it, it's also pretty straightforward, because we just take the dense node and then add the values where it should be. The thing which is a little bit more complicated is if we have got two sparse nodes that need to be combined, because then we need to interleave the values, see where there are overlaps, and then combine them accordingly. And this we can do in two different manners. So if we don't transpose any of the two matrices and they are sorted the same way, we can simply interleave them. That works quite well. If one of them or both of them are transposed, then we have to do a full sort. But the good thing is we can do it in shared memory again, because we control how we execute it. And in this way, we can also use the shared memory, which is on the multiprocessors, for being efficient. So, so much about the considerations that we have. We've implemented that, and probably I should mention that implementing any kind of algorithm in this format is actually pretty straightforward, because all you have to do is implement the functions which are responsible for handling individual nodes. So you don't have to consider things like what the memory layout of the final matrix will be, how you need to compute memory offsets, and so on and so forth, which is what you would have to do with another format. But in this case, all you have to consider is individual nodes or a combination of nodes when you have multiple matrices, and that's it. So it's actually pretty straightforward to write. And here's just a quick view on a few matrices that we tested the algorithms on. So you can see we have got quite dense matrices, quite sparse matrices, different sizes, different patterns, and so on and so forth. No need to go in detail, just showing you some performance. So the red one is actually ours. And then we have got HiSparse, CAST, and naive approach, which are these tiny axes, which are hardly visible, and HiSparse, which is a really optimized format. And this is for the sparse matrix vector multiplication. And I should tell you that the other algorithms are really, really optimized for that. So there's a lot of research on that, and the performance of them is really good. And what we are doing with our approaches, we actually traverse this hierarchy, right? So the other approaches just take the data, do some multiplication, add the things up locally, and then write it to the output. So that's pretty straightforward and it's really efficient. We have to traverse the entire hierarchy, then multiply the data and use atomic operations for writing the output. So that should be way slower. But if we take a look at performance, we are kind of in the same ballpark as the others. And there are some cases where we actually achieve reasonable performance, and the standard approaches, HiSparse and CAST, which are both from NVIDIA, they actually perform pretty badly. And we can then look how this looks like when we're talking about the transposed matrix, because I said we can transpose data pretty efficiently. And here you can already see that by just changing the indices within the leaf nodes, we achieve more or less similar performance that we had in these cases because we didn't change much. Whereas the other approaches have to explicitly compute a transpose operation. In this case, they lose a lot of performance for that. I'm not going to go into more detail here, just going to show you the results in terms of numbers. So this is the execution time in milliseconds. And you can see here our approach in comparison to the NVIDIA approaches and the naive approach, and you can see on average for the tested matrices we were actually faster than the others because of these special cases where they performed really badly. Right. And down here we have got really optimized approaches. So these are the block-based formats on the GPU which try to really align the memory in such a way that you can get really, really optimal performance. Where, for example, here you have got this 150,000 times longer pre-processing than the algorithm itself takes. And you can see that they are really beating us, but it's not more than a factor of 4. And for the transpose case, this is not even handled by the specialized formats. You can see that we clearly beat the others. And also for double precision, you see the same numbers more or less, or the same ratios. Okay, so much about SPMV. Also to show you the results for the addition. And here it's already pretty interesting because our approach is actually faster, as you can already see here, for the standard A plus B. Although we do all of the memory management and everything dynamically on the GPU and build a new hierarchy and all of that. And you can see the same here, the transpose case, it even gets more significant because we don't lose as much performance as the others. Although we lose a little bit because we have to do more sorting. And here is again the mean results, just to take a look. So we can see for single precision, we are significantly faster. In the transpose case, the ratios get even more significant for us. And for the double precision case, you can see the same. Okay, so probably I'll just give a quick summary about that now and check out how much time I will have left. Okay, as you can see here, what I want to say is that with this hierarchy format, we can actually go ahead and run the standard operations on the GPU kind of efficiently in the same kind of ballpark as the others. And for a lot of cases, we are actually faster. And we don't have any disadvantages when we transpose the data, which is quite common. And this means it's actually a good alternative for working with GPU for this sparsing algebra. And in the future, we will go ahead and actually take more complicated matrix operations on the GPU, for example, matrix multiplication, which is usually a really difficult case. Because with our hierarchy format, we think that is pretty well suited and we can tackle these more complicated cases. And also with such a hierarchical format, you can easily distribute the data between different GPU nodes, and in this way go to really large clusters more efficiently. Okay, so much about that. I've got another use case I will then probably quickly tell you. Any questions to that already? Okay. If there is nothing, I will go to the next one, which is representing and scaling procedural generation using operator graphs. This was a synchronization paper last year, I think, maybe 2 years ago. And what we want to do here is we want to run procedural generation on the GPU. Does everyone know what procedural generation is? It doesn't? Okay. The idea is that you want to go ahead and you want to generate geometry, but you don't want to do it manually. You want to use the computers to generate it for you, so you just come up with some rules or some kind of strategies how this geometry should be generated. So you start out with a simple geometry, a single seed, and then you say, okay, do this operation, followed by this operation, followed by this operation, and you will end up with some kind of complex geometry which you can then use. And you can introduce variations to that by altering the operations which are being performed. So this means you can generate entire forests, large cities, and so on and so forth. So that's the overall idea. I will go through it a little bit more quickly. Some use cases for it. Probably want to mention is games and movie industry. You want to go up New York. Of course, you cannot do it for real. So you want to go ahead and build a large city with a lot of buildings in the background, which you will not see in detail anyway. This is the perfect case for procedural generation. You just say, okay, here are my building footprints. Here is my procedural setup. This and this and this operation will lead to a building. Now introduce some variations to it with that and that, and that parameter setup. Build the city for me. Problem is usually this takes 2 hours, 3 hours, 4 hours, and then a designer might figure out, okay, that was actually not good. This one parameter, I want a tiny bit changed probably, and then you run it again. And then you wait for 4 hours and again see, okay, the parameter change was not like the idea. So this is one case where we really want to speed that up to have larger, have faster cycles of parameter testing and so on and so forth. Okay, and this is why I want to bring it to the GPU. People have done it on the GPU before. For example, L system generations, shape grammars for the GPU, and our work. And here, everyone used different scheduling strategies. So the L systems had large scaling overhead. The shape emulation with the graphics pipeline doesn't have enough parallelism and leads to thread diversions. And we didn't have a systematic approach before. We just went ahead and used some handcrafted grouping for the execution. So what I want to tell you now is how we tackled that problem and how we are trying to come up with the best way of executing it on GPU. And the idea is that we go to an intermediate representation, which we call the operator graph. And in this way, we can support different ways of writing these procedural approaches. So we can use L systems, which is just some rewriting grammar. We can use shape grammars, which are like have an object, do something with it, another object, or even some more complicated, more consequential operations that we just capture within the graph. And then based on this graph, we figure out how is the best way to map that to a GPU. And in this way, we found out that we can significantly faster than what we had before. And hopefully, we can even do it in an optimal manner, or maybe even prove our best way of doing it. Okay, I'm not gonna tell you too much about how we go ahead and cascade the operator graph. I will just show you a quick example of how a shape grammar could look like. So you would just come up with different rules, and you say you start with a box. You then split the box along the x direction, and then you into 3 parts, and you assign the first part to this rule, the second part to this rule, and the third part to the second rule again. And in this way, we can then discard intermediate elements, and you get this shape here, if you call that recursively, and this is called the mega sponge. So you can always see with just a really simple setup, you can generate more complicated objects. And then we would go ahead and take these individual operations. They become nodes in the graph, and then the way objects flow through this graph would be the edges in the graph. So the idea is you will start with some shapes up here. They would then kind of traverse through this graph. Different operations would be executed everywhere, and multiple objects might be generated, which then also flow through the graph. So this is the overall idea. And I'm just going to skip that example, and I'm just going to skip that example here, which just showed the layout system. Another question is, how can we go ahead and effectively execute these operations on the GPU? And the idea is that we have a couple of options. So we can, first of all, decide where and when we're going to execute which operations, and also where we store intermediate objects and shapes. And the storage can either be in registers or in this shared memory, which is on multiprocess, or in global memory. And this kind of allows us to change a lot in terms of behavior that is going on during the execution. And if you take a little bit closer look, the execution of the nodes are kind of the functions that are provided by the generation system itself. So you can have things like subdivide, split into multiple objects, move around, and so on and so forth. We cannot do too much here because it's just the operations which are to be executed. What do we do in between? Are we going to go ahead and, for example, have a couple of operations that we know are like always chained together and stay within the same thread for an execution? Or are we going to go ahead and run one operation, get some objects out, store them, for example, in global memory in some queues, and then reschedule the execution somewhere else? These are more or less the two options that we have. So if we stay always within the one thread, we're talking about a static scheduling, because we don't need to do anything. And if we go out into the queues, for example, using Whippletree again, then we talk about dynamic scheduling. And the interesting thing is that these scheduling decisions are exactly corresponding to the edges in this graph. And this means that we can go ahead and really figure out how we want to do scheduling by assigning either a dynamic state or a static state to the edges in the graph. And by doing that, we can then see that what we're getting is a partitioning of the graph, because if we have the static edges, things are kind of grouped together and we will stay within the same thread. And if we have got dynamic things, we need to go out. And this then gives rise to different ways of executing things on a GPU. For example, if you compare to previous work, if we assign all static edges, we would get this shape parameters within the pipeline. Interesting, there's a picture here. If we would use a grouping based on the rules which have been written by the designer, we would get what we had before. And if we would just use dynamic edges, we would get what people did for other systems. In this way, we have got an entire continuum where all of the previous approaches are just certain points. And now what we can do is we can not only try these individual points here, we can just go through this entire continuum and figure out what the best execution strategy would be. And for doing this, we can actually go ahead and come up with an optimizer. And in our first approach, we were just using a linear search for that, just testing all of the different options, which means for every single edge, we can either make it dynamic or static, which gives us many, many options, which is probably not efficient to test all of them. We came up with some heuristics to reduce the search space, but that's not so important. I'm just gonna show you some results to finish at the top. So, as you can see here, by searching for the fastest schedule, we always ended up with the performance that you can see down here. And you can see the different approaches, this single execution group, which was on the left before, this one execution group operation, which was on the right before, and ours, which was in the middle before, always is A, B, and C. So ours was our previous approach. and then you can see that you can always find the faster one. And you can also see here that of A, B, and C, the best performing one highly depends on what kind of problem you had. So for example, here strategy A does not work well at all, whereas strategy C works pretty well. And here, for example, A works very good, but B doesn't work well, and so on and so forth. And by always trying to look for the best schedule, we can find something better and can get significant performance improvements over the previous approaches, which actually showed these examples. So I guess the summary just says if you can go ahead and have some kind of more abstract definition of how scheduling can work on a GPU, and you combine that with a dynamic scheduling approach, you can actually go ahead and profile and optimize to figure out what the best way of executing this kind of problem is, and you can get significant speed up over the previous approaches. And that's it. Thank you very much. I hope it was kind of time.
Yes. Questions?
I have a question. Why is the, for example, the addition of two matrices with the transpose lower, which the standard methods, because you also only have to switch the indices.
Yeah, so I don't need to repeat the question. So the problem is that when you add two matrices, you generate a new matrix's output. And the usual format is the CSR format, where you have to sort the data according to the row indices. Which means what you have to do is you have to take all of the data from the two matrices. You would usually then go ahead and explicitly turn it into discreteless. You would sort them, and then you would have to figure out how many elements you have in every single row. You would then go ahead and compute the offsets for them, and then you would generate this new data as output. So this is kind of the slowest version of doing that, well, the way you could do it, and then having a transpose wouldn't make much of a difference. However, you usually do something a little bit more advanced, where you don't go ahead and generate the triplets explicitly, but you kind of know already that the both arrays are pre-sorted. And then you can more efficiently merge them together. However, when it comes to the transpose, the problem is you have got the row indices, for example, in this compressed manner, and the column indices explicitly. And as soon as you transpose it, you have to go to the triplet representation again. And this kind of slows everything down.
More questions?
You say that your data structure for this hierarchical approach uses up less memory, for example, for storing matrices.
Yes.
What's the overhead when processing the matrix, for example? Because I guess you also generate data on the GPU. How is that compared to other methods?
Yes, so this is actually where we then need additional memory, because we need to store intermediate information in these queues, right? So there's definitely more memory that we need. However, we can kind of scale this memory somehow if we do it in a reasonably smart way, which means we can provide larger queues. Then we don't have to try hard during the approach to stay within the memory. We just more or less go breadth first through the data and just throw everything into the queues, and we don't care. We just execute the database there. Then we get the best performance. However, if we want to reduce the memory, we have to do it in a little bit of a smarter way. And if we are about to run out of queue space, we have to go more depth first to not generate too much new data. And this can cost you because you might even idle then with some processes because you just don't have the output streams available, for example. So this is kind of a problem that you could face, that if you make the queues then too small, you might slow down your execution. But in theory, we can make them really small and still get a reasonable execution out of it, as long as we can somehow go depth first and actually end up getting data out of the queue. GPUs, so to say. It helps a lot if you use queues in this local shared memory, because then you kind of naturally get this step-first approach, right? Because you would just put the children into the local memory and take them out, and the next ones put them into the shared memory there. And if you then take them out from the shared memory in the right way, you kind of go that first. And in this way, you actually don't produce so much intermediate data. Of course, you then have to kind of find a good trade-off in actually putting tasks also into the global queues that you supply enough parallelism to be efficient. So there's kind of all of these trade-offs, and these are all things that we consider in when we go ahead and start the execution on the Numerical JKU. So that there's like many things you can do, and most often we have the kind of idea of which tasks will produce more work and which tasks actually drain the queues. And then, based on how much work we have in individual queues, we choose what to execute.
Okay, we have time for one or two more questions. I have a question. So, other communities obviously work on scheduling problems a lot, of course, in the context of operating systems. How would it work to run an operating system on GPU? Is it feasible? How do you see the perspective in 5 years from now?
First of all, scheduling on the GPU is quite different from the CPU, because you want to do everything like really largely in parallel, and all of the strategies that usually work well on the CPU hardly work well on the GPU. So this is something to note before. So for example, queuing algorithms, we thought, people have been working on queuing for a long time. Just take the best approaches that we know work for when a multi-threaded context, put in the GPU, we're done. However, it turns out the strategies usually don't work well, and you have to come up with alternative ideas because they are just too slow. This is one of the problems you're facing, and we already thought about like kind of coming up with a GPU operating system, because it would be really cool to have it, right? However, there's like loads of things which you just don't have on the GPU, so it's even really complicated to implement a lock, for example. And then you think about, okay, you want to support I/O probably, then you kind of have to be able to get data from the CPU to the GPU also. You have to get it back, you need communication there. You probably want something like a kernel mode, where you then support different operations, and then you have to deal with deadlocks. And on the GPU, you kind of always work against the hardware scheduler. So if you go ahead and use this approach that I told you before, where we just occupy the entire GPU, you also have to compile all of the functions into one big kernel, so you can dynamically switch between them. So you can always see that there are like quite a lot of things that you would want to work differently to have something like an operating system or GPU, because you just would want to go ahead and say, okay, here's a new program, execute this new program. But not possible, because you need to kind of have all within a big kernel. If you use dynamic parallelism, you have to have everything within the same context at least. So it's not so straightforward, and implementing logs, implementing a kernel mode, implementing I/O, it's like many small pieces that you would think should kind of work, but coming up with good solutions for all of them is not straightforward. And then the question is, what would you gain from it? And this is probably something which is holding people back the most, because there's not so much motivation besides it would be really cool to have it, but it's not like by having that we can now solve that, we can do that, because all you get is like, yeah, it's awesome, but.
So long story short, you don't think so?
Well, yeah, probably not, because there's just no motivation effort. And you would need a lot more hardware support. But GPU manufacturers obviously could do it if they wanted to.
Okay, thanks for a really interesting talk. This brings us to the end of our talk series this semester. So we have a summer break, and after the summer break, we start again with the talk from Stephen Feiner from Columbia University, which will be very interesting. And let's thank Markus again for this really interesting talk.